this is one of the hardest problems that people have tried to grasp in terms of how long it took to solve, and that's these 5 planets that you can see with your naked eye. You can see Mercury, you can see Venus, you can see Mars, you can see Jupiter, you can see Saturn. Tonight, just as it gets dark, the 2 brightest objects in the sky, in the south sky, are Jupiter and Saturn. Very rare that you get them in the same sky at the same time and so forth, but we've got them this summer and fall. These objects do funny things. So the Greeks knew that they were something different. They weren't like the stars. They look like stars to your eyes, but they don't move with the stars. So when you watch a constellation, the whole package of stars moves together. And sometimes the planet will move with them, and then all of a sudden for a few nights it moves the other way. You go, what the heck is that all about? Then it'll stop, then it'll move again, then it'll stop, then it'll it just kind of makes funny motions and so forth. So they knew that these things were very, very odd and so forth. And so, people over the centuries have been trying to figure this out, and you got people from Aristotle, 23 centuries ago, giving a stab at it. Ptolemy got closer about 20 centuries ago. You look at his model, and then all of a sudden Nicholas Copernicus in the 1400s gets even closer to the right end. And when you look at the data that Nicholas Copernicus has 600 years ago, it's within about 2% of what we would use today in terms of the distances from the sun to these planets. I mean, how did he measure that 600 years ago? So you kind of start thinking about that. He doesn't even have a telescope or anything like that at all. There's no devices such as that at all, so he's doing all the geometry and so forth. So Copernicus is getting closer to being able to predict the motion of these things, but the further you go out from the date that you're at, the more off his prediction turns out to be. So he's still kind of wrong. And really the reason that Copernicus is getting close is that he's putting now the sun at the center of the solar system. It's the first real modern sun-centered model of the solar system. We call that heliocentric. This is why he's getting close. But the reason why he's missing the answer is because he's got the planets really going around perfect circles, and they don't do that. His data is not quite good enough to see that they're not going circles. So the greatest naked eye astronomer of all time, Tycho Brahe, I think he's not that interested in this problem, but he has a beautiful laboratory in Denmark. So he's got a place to observe. He's got little slits in the wall where he can kind of see a star sort of, enter the slit. Then it sort of leaves the slit so he can measure times very accurately because he's not moving his head around. So he sees exactly how much of the sky it happens to move, and so he's getting velocities very, very carefully measured. His eyes are better than most people, so he sees more stars than most people do. And so when we look at his star maps of today, most people say, I don't even see these stars, but he is. So he's a very good naked eye astronomer, but he gets somebody interested in this planet problem, and that's Kepler. So Kepler and Tycho Brahe are working on this. Tycho Brahe is really doing a lot of the data, doing kind of the grunt work. And then Kepler is begging Tycho Brahe for the data, and eventually he gives it to him, when he's dying and that sort of thing. And it still takes Kepler about a decade looking at the data to see that the only way he can get the answer right for the motion of the planets is to have the sun at the center of the solar system, and they're moving just off of perfect circles. They're ellipses. But when I say just off, they're only like 2 or 3% off. They look like circles until you really start using measurement. And so when your things are in the sky, you're measuring not degrees that'd be you're way off. So you get 360 degrees, and you break a degree up into 60 parts, and those are arc minutes. And you break arc minutes into seconds, those are arc seconds. So you break a degree into 3,600 pieces. And he's off by like 2 or 3 arc seconds of circles. So it's small, but he says if you ignore it, then you're not really kind of doing the right thing. And so we have Kepler's, today we call these Kepler's laws of planetary motion, and there are 3 of them. And they give you the right motion for these planets and so forth. And Newton has those. And so this is 100 years before he was around. So So people got these rules of how these planets are moving, and the rules kind of read funny. Like the first one say, the planets move in eclipses. There's rule one. Rule two, might say something like the planet carves out equal areas at equal times. What the heck does that mean? But he's talking to people in his day, and if they're educated, the language of educated people is something like geometry. So everything is in terms of geometry. When a planet swings someplace in an orbit, and you measure it for a certain amount of time, that arc that it makes carves out some area. So if you really get something that is very eccentric, so if you have a certain center, and I make a real eccentric looking ellipse, if you watch the planet for like 1 month, like from right here to right there, say that's 1 month of time, and you go to the sun and you carve out this triangle has a certain area. Now later on, when the planet maybe is here, and you let 1 month pass, then maybe it's right there. When 1 month passes, then you make that triangle. This kind of squat fat triangle has exactly the same area as that one. Right there it does. And so you do this in terms of geometry. In today's world, we would say this is completely different, but we get the same results. We would say, well, when it's close to the sun, well, look at how much of the arc it does. It's going faster. When it's far from the sun, it's going slower. We would probably do it in terms of velocities and things like that. So, Newton has these laws in front of him. And, but we have no reason to suspect that we have any idea why they're doing this. No. So Newton's going to give us this name. He says, okay, there's this force between the sun and the planet. And that force I'm going to call gravitation. So now we have a name for it. How do you calculate the force of gravitation? And he says, well, the sun is the controlling object. Everything's going around the sun because it must have the most something. And this is going to be inertia. That is hardly moving, so it's mass. And so Newton is saying something like the force, I'll put a capital G here, gravity, is somehow proportional to how massive these objects happen to be. So it doesn't matter what the objects are, the more mass they have, the more gravitational force they put on each other. So this is what a proportion is. When these are big, and that one's big. But there's also then this distance. When they are far from each other, I really want the force to be small. When they're close to each other, I want the force to be big. That sounds like they're not proportional, but inversely proportional. When the distance is big, I want the force to be small. And so the distance, your textbook uses R, it looks like a radius, but it's really a distance from center to center. When this is big, the force is small. Now, Newton knows that this distance here has to have a square on it because he has Kepler's laws in front of him. So, if you have Kepler's laws in front of you, you see exactly why the distance is going to be squared. And so, kilograms times kilograms divided by meters squared does not give you newtons at all. So you're off by a constant of proportionality. And so Newton just called that capital G, and we use capital G ever since Newton. But this is just the masses of the two objects, these M's. M1 and M2. These are just the masses of the two objects. And it has to be kilograms. This R is the center to center distance. Between the objects. And capital G is a constant. It's just like saying that the circumference of a circle is proportional to its diameter. The circumference is not equal to the diameter. They're not the same number, but they're proportional. When the diameter gets big, the circumference gets big. You're always off by this factor of 3.1415924, blah, 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 and then my goes on forever and so forth. And so this is a universal constant here. And so we call this the universal gravitational far as we know, if you go to the moon and you draw a circle and you get the circumference and you divide it by the diameter, you come up with 3.14. You do that here on Earth anywhere, you get exactly the same results. And we kind of think no matter where you go, if you draw a circle, you measure the circumference, measure the diameter, you get one divided by the other, you always get exactly the same thing. We right now believe that no matter where you are in the universe, if you get two objects, separate them by a certain distance, you will always get the same force between them as if you did it here on Earth, which means that G is the same value all over the universe. You get to see this somehow play out differently in different parts of the universe and so forth. This is a number that is needed. It has to have the right units so that it has newtons equals newtons. And it has to have the right value so that we actually get the right value for the actual force and so forth. This is something that Newton had no idea what the value was. He just knows you're off by this constant because he can't do the experiment. You can get two masses, that's easy, and the other masses. You can separate them by a known distance, that's easy. But then you have to measure the force, and then you can solve for that. If you get two objects, like two bowling balls, and you suspend them by threads, you actually see them go together. You actually see the force on this planet take place. The force is so small, we don't see objects do that. Well, why not? But just the air currents in the room are bigger than the actual force of gravitation. So it's a very difficult experiment to do. There is a force between those two things. They really want to move together, but to really do the experiments, you almost really kind of want to be in outer space. That is away from the planet, because that's the big object that's acting on Earth. Get away from the planet and have no friction, no air, and set two bowling balls there, back off, and then watch what they actually do and so forth. It's going to be 100 years after Newton at Cavendish that Cambridge University is going to show up and do the experiment. They'll get two objects, separate them by a distance, and be able to measure the force between them. And it's tiny, very, very small. Something like 1 billionth of a Newton or something like that for objects that we have in the classroom and so forth. And so today we call that a Cavendish balance. I've got one, my physics 102 students just did a couple weeks ago. We were about 3% off from what today would be the accepted value and so forth. But you do the experiment on your glass because they, like I said, the air and stuff is a bigger force and so forth. So this thing has got the same value all the time as measured by Cavendish. And when he did that, we say that Cavendish weighed the world. And what in the heck is that? Well, I'll show you here in a moment. But G has this value, and we believe it's the same always. 6.67 times 10 to the minus 11. So it's a very small number. It has to be carrying newtons with it. It's got to cancel out meters squared on the bottom. It's got to cancel out kilograms squared on the top. So it's got to be carrying those units. So you've got you have meters squared down here. It's got to cancel the meters squared down. You got kilograms squared here. You got to cancel out the kilograms squared with that, and then you have newtons equals newtons and so forth. Now, two things about this law. One is it's called the universal law of gravitation. And what we mean by it's universal, we really believe any objects that have this property called mass are exerting forces on each other because they have this mass. So if you have mass, the wall has mass, does this mean that somehow you're attracted to the wall? That's exactly what this force says. You are attracted to that wall. Oh, but you're also attracted to that wall. You're also attracted to that wall and that wall. You're attracted to the stuff above you, but it's not too exciting to think that, well, I'm going to move towards the wall. Well, no, because there's just a big giant thing underneath it, right? And so that Earth is really the big force. And the friction between you and the wall is just way too small for us to see you accelerate towards the wall or anything like that whatsoever. So it's universal. It's between all objects. And it's an inverse square law with distance, inverse square. When the distance gets big, the force gets small. When objects are far from each other, they don't feel each other. That makes sense. Jupiter's big, but it's 500 million miles away from you. You're not worried about it tugging on you. The moon is small compared to Jupiter, but it's close. And does it tug on you? Well, yeah, it's what gives us the tides every day. So it is tugging on the Earth and affecting things around us and so forth. But if I were to double the distance between objects, if this got twice as big, 2 squared in the bottom gives me a 4. The force goes down by 1/4. If I triple distances between objects, 3 squared gives me 9 on the bottom of this number. The force is 1/9 as big. The gravity force dies off very fast with distance. So when you're far from something, gravitationally it has almost no effect on you. But it doesn't quite go to 0. It only goes to 0 when really the distance goes to infinity. But the force is very, very small at distance very, very quickly. Now, to use something like this, what if we just got like 2 bowling balls, for example? Let's say you have a bowling ball here. Let's say it's 5 kilograms. That's about a 10-pound ball or so. And from center to center, let's say we got a little kitty ball over here. Let's say this one's 3 kilograms. And let's say that, you know, this distance right here, actually from center to center is what, about probably like 40 centimeters or so. Let's say they're 40 centimeters apart. Newton is saying that there is a force between these 2 objects, and you calculate it according to this. Forces are the big deal. All objects maintain their velocity forever unless you put a force on them. Here's a force of nature. You put a force on objects, this changes objects' motion. He's telling you how to calculate it. That's extremely important. And so, yeah, the force is really only going to be big though if the distances are really small or if the masses are giant. But between 2 bowling balls, there should be a force here. For the most part, I need to go to my calculator to probably do most of this. So G has a value of 6.67 times 10 to the minus 11. That's newtons. That's meters squared, kilograms squared. I'm going to multiply by the mass of one object, 5 kilograms, by the other object's mass, 3 kilograms, and divide it by how far apart they are on the bottom squared. And that's it. Now, some of your calculators will like this, and calculators will not like this. Let me try my calculator. And if you're not doing the same thing, then your calculator doesn't like it. I think I get 6.3 times 10 to the minus 9. So I'll round that to 6.3 times 10 to the minus 9 newtons times 10 to the minus 9, a billionth. This is about a half of a billionth of a newton, and forces are numbers and their directions. Which way is the force? The best you can do is say this is always an attractive force. This force is toward, each other. That is the force of gravitation, the number and the direction. The force is tiny. Now, if I change objects, then the force starts looking a little bit more important and so forth. So, if you have a bowling ball sitting next to another bowling ball, there's like a billionth of a newton between them. Like friction is way bigger than that. Air currents are way bigger than that. We're not going to see this force play itself out unless you've got something like the Cavendish balance where you can get rid of a lot of these other little forces and so forth. But now, let's open up to the front of your book, and I start seeing some stuff up in the front. Big objects. Useful data. And so I start seeing, the mass of the sun and so forth. So, what if one object, for example, was the sun, and the other one was the earth? The sun, looking at right in the front of your book here, has a mass of 1.99 times 10 to the 30 kilograms. That's the heavyweights. looking at the mass of the Earth. Right above it. 5.98 times 10 to the 24. 6 powers of 10. Earth is 1,000,000 times lighter than the sun happens to be. We also need the distance between them. So, Earth, Sun distance 1.49. So he's got it right there. So I'm going to calculate the force between the Earth and the Sun. Force, Earth and the Sun. That's going to be 6.67 times 10 minus 11 newtons times meters squared over kilograms squared times the mass of one object times the mass of the other object divided by how far apart they are squared. And so the Earth-Sun distance, he's got 149.6 times 10 to the 6 kilometers. So I'm going to change that to meters immediately. So kilometers, 10 to the 6 kilometers is, I guess, I got to add 3 powers to get that into meters, and that's, the distance has to get squared. So, that is the force that the Earth and the Sun are exerting on each other. So I'm going to go to my calculator and see exactly what I get for this. 6.67. Times 10 to the 22. So this is
Yeah.
yeah. Oh, times 10 to the 22. That's so big we don't have a name for it. Millions are times 10 to the 6. Billions 10 to the 9th. Trillions 10 to the 12th. Quadrillions 10 to the 15th. This is 10 million quadrillion newtons.
If the moon affects us in a smaller, do we affect the sun? Oh,
Let me ask this question. Who's exerting this force? On each other. Both are. Is that what you're asking? There's a little object here, there's a big object here. Who's exerting the force? What's third law? Object A puts a force on object B puts the same size force on object A, they just happen to be in opposite directions. This is the force they put on each other. The big one does not exert the force or anything like that. This is the force that is between the Earth and the Sun. So, the Earth is quite a bit heavier, more massive than the Moon. Is it proper to say that the Earth exerts the gravity force on the Moon? No, they put the same size force on each other. Same size force on each other. Is that what you're asking? The force is shared between the two. The Sun, in the picture I've got up here, the force is to the right. On the Earth, the force is to the left. That's the magnitude of the force, that's the size of the force, but it's attractive. This force, as far as we know, is always attractive. Oh, Newton has a way of calculating this force. Now, if this force is not coming on your calculator with that correct power of 10, then we have to figure out exactly why your calculator doesn't like it. Because it can do this problem. It's just a matter of being able to use it the right way to do this. So, this is a big deal or not? one of the fundamental forces of nature. And Newton is telling you exactly how it behaves mathematically. Exactly. This is how you find the force between any two objects, just because they're there. Because they're there, they attract each other. This is a big deal, right? Because if you understand forces, you understand everything's motion, theoretically, because F equals ma. Have the forces, whatever's left over is how the thing's going to change its motion. You know everything about that object's motion that you need. If you can figure out the forces, and you say, well, this is how you figure out the forces of gravitation. Now, here on Earth, it's probably not a huge deal, or is it? No, let me think about this. The first law that you saw in this class, the law of falling bodies. It says what? Do you have it exactly?
Disregarding air resistance, all objects will fall with the same constant velocity.
Acceleration.
Acceleration.
That's good from Galileo. Galileo is preceding Newton by like 1 day or something like that. He died when he was born next day. The law of falling bodies. All objects, if we can disregard air resistance, fall with the same acceleration. It's something that Galileo is measuring and observing. He does not know why it's true. Does not know why it's true. Newton does. How does Newton know that why this happens to be true? Up until now, we know how to calculate the force of gravitation on an object, right? We call it a different word. Weight. Weight is the same as the force of gravitation, force of gravity between object and a planet. The weight of the object is the mass of the object times acceleration due to gravity. That's why we've been doing that. Newton has another way of calculating forces here between two objects. And that is capital G times the mass of the object times the mass of the planet divided by how far apart the object is from the planet. That's the center to center distance. So, if you're on the surface of the planet, how far are you from the center of the Earth? Wouldn't that be? So if the object is you, how far are you from the center of the Earth?
Radius.
That's kind of the radius of the planet. Squared. Law of falling bodies is explained with me doing this. Slash, slash. That is the law of falling bodies. the mass of the object cancels out. G for any object is calculated, this is little g, as capital G times the mass of the planet divided by the radius of the planet squared. It's independent of the mass of the object altogether. So G of any planet is capital G, the mass of the planet, times, or excuse me, divided by the radius of the planet, squared. It's independent of the mass of the object. All objects will have the same acceleration because this is going to cancel out all the time. That is the law of falling bodies. They all have the same acceleration, independent of the object's mass. Depends on a constant. The mass of the planet is probably not changing. The size of the planet's not changing. This calculates some sort of constant number. When Cavendish actually measured capital G, people said that he was weighing the Earth. Now, when I take a look at what's in the front of your book, we have a value for the mass of the Earth. Where did we get that number? The scale of the Earth. There's nothing to hang the Earth from to find out how much mass it has. But when Cavendish did his experiment, we say he basically weighed the Earth. Cavendish's experiment measured capital G. Once you've got a value for capital G, then we can do exactly what we've got right here. G, the mass of the planet, divided by the radius of the planet, center to center distance squared. In 1800, does Cavendish know G, little g, for our planet? Yeah, Galileo did that 200 years before, 1600. That's 9.8 meters per second. Cavendish knows that in 1800. He knows that that is 9.8 meters per second. He measures in an experiment the value for capital G, 6.67 times 10 to the minus 11. That's newtons, meters squared, kilograms squared. What we don't know in 1800 is the mass of the planet. In 1800, do we know the radius of the planet? Yes, we know that in 1800, right? We know that 2,000 years ago, you just put a stick in the ground, look at shadows, and get within 2%, right? Aristotle did that about the year 0 or something like that. So we know the radius of the planet for a long time. I always forget that number, but anyway, we just always look it up. So he'll have that in front of your book. So Aristophanes measured that the Earth's radius is 6.38 times 10, and he's got it here, Earth radius in kilometers, times 10 to the third kilometers, so times 10 to the 6th meters, and that distance gets squared. This is how we have a value for the mass of Earth in the front of our book. So we've measured G experimentally, we've measured capital G experimentally, we've measured R experimentally. This law says that that mass of the planet has to be sitting right there. So I'm going to get this multiplied by that, divided by that, and that should be the mass of planet Earth. And then this is where you're hoping that you do the algebra right and stuff, because it should not be what's back in the book. Don't forget to square that. Divide by 6.67. Minus. And yeah, so I think when I put these numbers in my calculator, I get the mass of Earth is 5.98 times 10 to the 24 kilograms. So that number times this squared divided by that, there's the mass of planet Earth. So
That's where the number in the front of your book comes from. There's no physical way to actually measure this. It's trap it in some sort of law and measure everything else. Suddenly, with Newton's law of gravity, it doesn't look like some sort of little trivial thing that could just explain, what the planets are doing, whatever. It's telling us the mass of the planets. Suddenly, it's explaining the law of falling bodies. It seemed like last week, when we started this discussion of things going in circles, we came up with a number of how fast something has to go to get orbit around the Earth. What was that number?
Like 88.
It was like 8,000 meters per second, which is 8 kilometers per second, which is 5 miles per second, and so forth. So you have to make something go 5 miles a second, otherwise it's going to come back down to the Earth. Newton would be able to, if he had enough experimental results in front of him, know what the velocity for a stable circular orbit would be. Velocity for a stable circular orbit. You put an object into space around the Earth, there was something pulling on it, the force of gravitation. It wants to fly in a straight line, but gravity is the only thing that exists that can make it actually go into a circle. So gravity causes circular motion. Gravitation causes circular motion. That is the creator of centripetal force. You've got this right here, Earth. Here's your little satellite, and you're making it do something like that. There's only one force on this thing. It wants to do this. It wants to go in a straight line, but there's something pulling it towards the center of the circle. It's the force of gravity. The force of gravity is the cause of the centripetal force. This right here is calculated. Here's the mass of your object, the mass of your planet, divided by, this is the distance from the center of the planet to the object. This is not the radius of the planet. R stands for the distance between the two. So this is R, the size of the circle the thing is making. And if that is creating a centripetal force,